Hi, good morning everyone. Welcome to our third tutorial for analog electronics TE 205, and our third tutorial will be on power amplifiers. Okay, we have few subtopics that we will discuss today. Okay, for the objective, we will go for the quiescent Q point, and also we will discuss on few different classes of power amplifier. We will go for class A, class B, class AB, and class C power amplifier. Okay, for this Unit 3, we will discuss on circuit of power amplifier, which covers the analysis of class A, class B, class AB, class C power amplifier circuit, and we will also discuss on the distortions of amplifier and power dissipation issues, okay, at the end of each section. Okay, and what is actually power amplifier? Okay, it is basically the large signal amplifier, which is different from the small signal amplifier discussed in previous tutorial. Okay, basically we have covered in tutorial previously, tutorial 2 and also tutorial 1, and also you have learned on the BJT transistor circuit for analog electronics in fundamentals of electronics. Okay, for this power amplifier utilizes a large portion of the load line. Okay, it is used to deliver high power to low resistive load. Okay, thus the analysis of the power amplifier is not the same as its corresponding small signal amplifier counterpart. And the power amplifier is normally used as the final stage of a receiving or transmitting system. It can be used to provide signal power to, for example, we have a speaker of typical, we have 4 ohms of resistance, or if we want to transmit signals at transmitting antenna of typical, for example, we have value of 300 ohm resistor. Okay, that is for the transmitting part. And ideally the power amplifier would deliver 100% of the power it draws from the DC supply towards the load. In practice, this case will never occur because some of the components in the circuit in the amplifier are dissipating power. Thus, we have a term named as the power efficiency. Okay, and we can get the power efficiency by using the formula of this is for power efficiency. Okay, for power efficiency, this formula PAC over PDC, okay, multiply by 100, or we can have PR over PDC. Okay, multiply by 100. This is the efficiency for the power amplifier. Okay, what is the Q sign? Okay, quiescent point or Q point. Okay, Q point of various class of power amplifier is drawn on the DC load line. Okay, we have for example here, okay, this is AC and DC load line. Okay, and the intersect, this one is AC load line, and this is the DC load line. Okay, and the intersect between this AC and DC load line, we call it as the Q point. Okay, there are different power amplifier will have different Q point value. And this is the DC load line we have here. At the axis X is the IC collector current value, and at this Y is the voltage common emitter. Okay, for voltage common emitter voltage. And here this is the lines for base current. Okay, base current value. Alright. For example, let's say we have this circuit, common emitter amplifier with a BJT here. We have BJT. This is base. Sorry, this is collector. This is base, and this is emitter. Okay, remember we have learned on this in previous subject in BJT. Okay, we have studied in bipolar junction transistor amplifier circuit that if the Q point is not centered, the maximum power would not be delivered for the amplifier. This is because it limits the maximum collector current at the collector. Okay, and the collector to emitter voltage between here we have VCE. Okay, VCE swing. Otherwise, clipping and cut off, clipping at the cut off and saturation at output due to being overdriven by the input signal will occur, which is we call it as the distortion. Okay, the non-linear distortion caused by large signal swing. Okay, so from this common emitter circuit, okay, so we can get the DC or AC load line. Okay, this figure A here is the AC equivalent circuit, and figure B is the AC load line. Okay, this is the AC equivalent circuit for this common emitter. Alright, and this is the DC load line. Okay, the load line. Okay, how to get the load line? It is actually the components that related is the collector current and collector to emitter voltage. Okay, this is at saturation and this is at cut off. This is at saturation and this is at cut off. Okay, how to get that actually? Okay, the DC load line is determined by the VCE at cut off. Okay, so at the VCE actually the IC is equals to 0. Okay, the value of IC is 0. Okay, at the cut off. Okay, how to get that? It is actually we have to apply the KVL inside here lah. Okay, we can this way or this way to get the IC and also to get the VCE. This is the important parameter in DC analysis. Okay, we have 3 loops that we can go here. Okay, for voltage divider. Alright. And at the saturation, the VCE is equals to 0. Okay. So this is the Q point. Okay, we have the blue one, the AC load line, and and the red one, this the DC load line. Okay, for both the load line, you can get for AC load line calculated based on the circuit, this one. Okay, based on this one here, we have to determine to get the parameter based on the small signal model for AC load line, AC analysis. Okay, and for DC load line, this one is from AC analysis, this one is from DC analysis. Okay, and this is the intercept, we call it as the Q point. Okay, Q point is the essentially the operating point of the transistor. Okay, next we go for the power amplifier. Okay, the covered for this unit 3 includes the analysis of class A, class B, class AB, class C power amplifier circuit. Okay, the analysis of power amplifier is not the same as its corresponding small signal amplifier counterpart. And power amplifier is basically the large signal amplifier, which is different from the small signal amplifier as earlier. Power amplifier normally used as a final stage of a receiving or transmitting. Okay, ideally, power amplifier would deliver 100% of the power it draws from the DC supply to the load, but in practice, we can never occur because some components of the amplifier we have dissipating factor. Like previously, I have mentioned, we have power efficiency is equals to P out over PDC multiply with 100, or AC power output power over DC input power. Okay, multiply by 100. Okay, first we go for class A power amplifier. Okay, so class A, when an amplifier, irrespective of a common emitter, or we have few configurations. Remember, we have common emitter, common collector, or common base configurations. Or also we can have the transformer coupled. It is biased with an input signal such that it operates in the linear regions for 360 degrees of the input cycle in a class A amplifier. Let's see, we have a figure here. Okay, this is signal, input signal for class A. Okay, for this maximum amplitude for input signal, and then when it goes inject into a power amplifier, we can have this output signal with this amplitude for one cycle. Okay, look here. First, for the input signal, this is part for first half cycle is positive cycle. But now here we have negative cycle, meaning that it is 360 degree changes. Okay, it's kind of mirror from the input signals. Okay, so this is for class A power amplifier. This is a circuit for class A power amplifier. Okay, this is for common emitter. Okay, for this one, for DC and AC load line of this amplifier are different because they do not have the same equivalent circuit. Okay, for DC, AC and DC load line. Okay, this is for class A power amplifier. The important parameter that we need to get. Okay, for the voltage gain, how to get this one? It is from the small signal equivalent circuit AC analysis. Okay, AV is equivalent to V out over V in. Okay, V out is at this part, V in is at here. Okay, and the voltage gain of class A amplifier is determined the same way as the small signal amplifier, with the exception of the formula used as AC emitter resistance. Okay, because for small RE, it is not valid for large signal amplifier. So we don't have the value for this small RE inside this formula for voltage gain here. Okay, and remember for the AC equivalent circuit, for here we have the capacitor. Okay, for AC equivalent circuit, the capacitor must be short circuit. So meaning it is bypass capacitor here. Okay, so there is no RE. Okay, so the same goes here is short circuit. So that is bypass capacitor for C3. Okay, and for power gain, AP is equals to AI over AV. AI is the current gain, meaning that I out over I in. Where the large signal current gain AI is approximately equals to DC beta, beta DC, or also equals to alpha RC over small RE equivalent to RC equivalent to RE. But then we don't have this RE value, so we use the value for beta DC. And the power efficiency, okay, we can have these expressions for class A power amplifier. Remember, this one is fixed value. Okay, this is also the maximum power efficiency of class A amplifier, since P out is maximum value. Okay, in order to achieve higher power efficiency for class A amplifier, we apply the transformer coupled class A amplifier. Okay, this one we design the class A amplifier with transformer coupled here. Okay, owing to the presence of counter EMF in the transformer, when the AC VCE drops to minimum value, the voltage across the primary coil is equal to VCC. This one here, okay, equals to this value. Okay, and this one is also the circuit for common emitter. Okay, the DC resistance of the primary coil is normally very small, which can be less than 5 ohm, and the value for RE here is normally small for power amplifier. Okay, the voltage at collector of the transistor is approximately equal to 2 VCC, and thus ideally the AC VCC maximum is equal to 2 VCC, and AC IC saturation is equals to 2 ICQ, and DC VCEQ is approximately equals to VCC. Okay, that is how we can get the efficiency of the amplifier. Okay, double from this, the first one, it is only 25%, so now we can get the 50%. Okay, ignoring the current flow in the voltage divider network. Okay, this one, this is, we call it as the voltage divider, and we have the maximum power P out is half VCC ICQ, or half VCEQ ICQ. Okay, and the DC power supply, we have a PDC equals to VCC ICQ. Okay, next one we have a class B power amplifier. Okay, when an amplifier is biased such that it operates at the linear regions for 160 degree in the cycle, and it is in cut-off regions for 960 degree, so we have this one is class B power amplifier, and this is here is the output for input and output for class B power amplifier. Okay, originally we have this input signal, same with the class A power amplifier. Okay, for this input signal, positive and negative cycle. Okay, positive and negative cycle. And this one, after go to class B power amplifier, we have these types of output for class B amplifier. Okay, it is biased at cut-off region so that the ICEQ is equals to 0. And VCEQ is equals to VCE cut off 480 degrees of the input cycle. So we have positive cycle for 180 degrees only. This is circuit for class B power amplifier. Okay, we have two for positive and negative cycle. Okay, we have two transistor in the circuit. One is Q1 and Q2. Okay, we'll have at one for positive cycle and another is for negative cycle. Okay, the circuit here shows a push-pull class B amplifier which utilizes two emitter follower and act as complementary amplifier. The reason for complementary is because one NPN and other PNP which conduct an opposite alternations of input signal. During positive cycle, the NPN is conducting while PNP is cut off. This one, it is this is NPN and this is PNP. So Q1 is on, Q2 is off. Okay, and during a negative cycle, this NPN is off and PNP is on. Okay, the PNP is conducting and the NPN transistor is cut off, so we get this negative cycle. Okay, for output. Okay, when no DC bias for amplifier circuit, the positive cycle of the input signal need to exceed VBE of the NPN before conducting can occur. Likewise, the voltage of negative input cycle needs to be less than minus VBE before the PNP would conduct. Okay, remember what is the value for VBE? It is 0.7 watt. Okay, for VBE. Okay, we have this region here where both of Q1 and Q2 off. Okay, or we call it as the crossover distortion. Okay, so circuit of class B amplifier has dead band problem. It is replaced by class AB. Okay, this is, we call it as the crossover distortions or dead band. Okay, thus there is a period of the input signal where there is no conductions for both NPN and PNP, which termed as dead band. Okay, the period of the time would cause distortion called crossover distortion. Okay, how to overcome that? Okay, we introduce class AB. Okay, this is a circuit for class AB amplifier. Okay, this one is common collector configuration. Okay, class AB amplifier is biased to conduct slightly more than 180 degree and utilizes two transistors where they are alternatively turned on and off. Okay. Thus, this is the reason it is also named as push-pull amplifier. One of the technique is to make both transistors slightly above cut-off when there is no AC signal. This can be achieved by voltage divider technique as in the circuit this one. Okay, for this voltage divider technique. However, this arrangement is difficult to maintain due to VBE value or VEB variations caused by temperature. Okay, it is caused by temperature for the value for the excitation for the diff current. Okay, a stable technique called diode clamping. Okay, this is because this one we call it as the diode clamping. Okay, we have two diode D1 and D2. Replace the R2 here. Okay, this is because the characterization of the diode is closely matched with the transconductance of the transistor characteristics. Okay, so we have these two diode D1 and D2 for diode clamping in class AB power amplifier. Okay, this is analysis for class AB power amplifier. For the power efficiency, we have the maximum AC output power, okay, P out, okay, V out RMS. This is fixed value, yeah. Okay, just the changes in here, VCEQ and IC saturations. And since VCEQ is, we know this value, so we have P out is 0.25 VCC IC saturation. Okay, the DC input and PDC, we have VCC ICC. Each transistor is only driving current for half cycle here. Okay, half cycle and another half cycle. Therefore, the current is half wave signal, which is average value of ICC. Okay, we have the IC saturation over pi, and we have PDC, VCC, IC saturation over pi. Okay, for half cycle. It is not 2 pi, only over pi. Okay, for a non-ideal class AB push-pull amplifier where VCE saturation is not equal to 0, then we have the VCEQ maximum is VCC minus VCE saturation over 2, and we have IC saturation is equals to VCC VCE saturation over 2 RE. And we have the DC input power, PDC, is VCC, ICC, and each transistor only drawing current for a half cycle. Therefore, the current is half wave signal with an average over pi, this one here. And this is the efficiency for class AB push-pull amplifier. This is class AB. We can get this. Okay, better than class A amplifier. Class A is 25%, class A with transformer couple is 50%, and class AB we get 78.5%. Okay, so next one we have class C power amplifier. Okay, it is biased so that the conductions occur for much less than 180 degrees of the input class, as we can see here. Okay, this is the input signals and this is the output signals. Okay, the amplifier is more efficient than class A or push-pull class AB amplifier, but then it has limited applications as tune amplifier for radio frequency. Class C amplifier showing its input and output signal. Okay, normally we apply class C power amplifier. in RF transmitter, RF amplification, this one is for communication, broadcast, and RF signal generator. Also in oscillator, constructions of due to ability to provide high gain. High gain at specific frequency. And also in some medical equipment. Devices that requires RF. Energy, such as certain types of diathermy machines, for therapeutic heating. Meditation. This is a basic common emitter class C amplifier with resistive load. Okay, basic class C amplifier. It is biased below cut-off, which negative VBB supply. We have VBB or VCC supply. The input AC source voltage has a positive peak value slightly greater than absolute value of VBB plus VBE, so that the base voltage exceeds the VBE of the transistor for a short time near the peak, while the transistor is total cut off during negative cycle of the input signal. So we have VBB. Okay, the power dissipation of the transistor in class C amplifier is low because the transistor is turned on for only a small percentage of the input cycle. Okay, for example, here we have the input and it will only turn on at this period only. Okay, this the collector current pulses and the time between the pulse of the period T of the AC voltage. Okay, so this is for one cycle and only turn on at this period only for waveform of class C amplifier. Okay, so this is a tuned class C amplifier and waveform. Okay, so this is for the V out. What is the difference from here? This is for class C amplifier and this is a tuned class C amplifier. That we have this circuit, additional circuit here to get this waveform. Okay, so owing to the fact that the collector voltage is not the replica of the input signal, the resistively loaded class C amplifier alone is of no value in linear applications. It is therefore necessary to use class C amplifier with parallel resonance circuit, or we call it as the tank circuit, this part here, Okay, the short pulse of collector current on each cycle of the input initiates and sustains the oscillations of the tank circuit so that the output sine wave voltage is produced as we can get here. This is for positive cycle and the output. Okay. Okay, for the maximum peak, we get the minimum peak here. Okay, and this is the basic class tune amplifier with tank circuit. Okay, and owing to the charging and discharging of the capacitor in the tank circuit of C2. Okay, what is the characteristic of the capacitor? Okay, it can store energy, and due to that, it will be charged and discharged. Okay, through inductor L. Okay. Charging and discharge of the capacitor C2 through the inductor L. The peak to peak output voltage is approximately equal to 2 VCC. Okay, for here is approximate to 2 VCC value. Since the voltage developed across the tank circuit has a peak to peak value of approximately 2 VCC, then we can get this expression. Okay, maximum output power can be expressed as this one here. Okay, RC is the equivalent parallel resistance of the collector tank circuit and represent the parallel combination of the coil resistance and load resistance. Because we replace this one with this one. Okay, so the RC value. Okay, the total power that must be supplied to the amplifier is P total. Okay, total is equal to P out and PD average. And the efficiency of the amplifier, we can get this one. Okay, when P out is much more greater than PD average, the efficiency of class C amplifier reaches 100% of the efficiency, and PD average is the average power dissipation.